Okay, hello again to everybody. So the next talk is with Professor Dalibor Froncek from the University of Minnesota, USA, Duluth. But he say us that this is a conference with six invited speakers, but at least 7 countries, because our Professor Dalibor is from Czech Republic. So we can consider that we have 7 different countries at the moment. Yes. So I meet Professor Dalibor in a conference in his honor in 2023 that was organized for our common friend and colleague Sylvia Szyczak from the Krakow University, and it was a very magic conference. You will see, I hope, maybe, that Dalibor is very magic mathematician. I don't know. We will see in your conference. And I know that he likes barbecue, beers, and he likes to hear about histories of life. Yes? So I am very happy that you accept our invitation as invited speaker. So thank you very much.
Thank you for your introduction. Let me share my screen. So, okay, can you see it now?
Yes.
Okay.
Yes.
So let me just change the settings here. Okay, well, okay, everything disappeared now.
Yeah, everything disappeared.
No, on my screen, everything is just disappearing. Okay, here it is. No. Anyway,
it's fine.
So can you see my screen now?
Yes.
Yes.
But you don't have full screen.
Yeah, it's not showing where I was thinking it would be showing, but anyway. So
Okay.
As you can see, last minute I added my Czech affiliation to support the claim that we have more countries than speakers. So Combinatorica is a little non-profit organization that supports research in combinatorics. More specifically, it supports my research in combinatorics because I'm the owner of the non-profit organization, and I use it to launder money that I get from the Czech Football Association for doing schedule of the Czech professional soccer league every year, and to avoid paying taxes, I put it in the non-profit, and then I pay my conference attendances using the money from that. So I'm not having income, I'm just paying for my professional development. I'm saying that just in case that, some kind of tax administration is listening now. So what I will be talking about is not magic this time. I have 2 main directions of research. One of them is magic type labelings, and the other one is G designs or graph decompositions in general. And this is a joint work with my students. Danny was a graduate student, and Aidan is my current undergraduate student, and Andrew Seilstad was my student. He started his research with me when he was actually a high school student, and he was taking my graph theory class at UMD. Now he's at the University of Minnesota, Twin Cities. So let's start with a definition of a G design. So what it is, basically, I have a complete graph on n vertices, and I want to put in several copies of the same graph. So I will have isomorphic copies of the same graph such that every edge of my complete graph appears in exactly one copy of that graph. Here is an example of a decomposition of K8 into a graph consisting of 1 4 cycle and 3 hanging edges. Forget the notation, it's taken from another presentation where I needed the vertices to be labeled as in bipartite graph. So here is an example of what we mean by that, and we will go through the rest of the definition later when we need it. So let me give you some background about where we stand with small G designs, decompositions of complete graphs into small graphs. When I was first time preparing this presentation, that was the current state of the art. Graphs with at most 6 edges, there was one little exception, which is no longer the case because Andrew Seilstadt and we solved it. So graphs with at most 6 edges are all known when they decompose the complete graphs. And of course, next you would think would be 7 edges. However, there is more known about graphs with 8 edges than 7 edges. There, almost everything is known except for a few exceptions. And these should be solved, and maybe Brian Freiberg and his students are already working on it. Brian Freiberg is my colleague at UMD, who also works in magic type labelings and graph decompositions. Why 8 edges is better known than 7 edges is the following theorem. Of course, we have a necessary condition if we want to decompose a complete graph into a graph with m edges, then the number of edges must divide the number of edges in the complete graph. And for powers of 2, the spectrum where the divisibility condition is satisfied is simpler, it's easier than for 7 or anything that is not a power of 2. And I will talk about it in a little bit more detail later. Here with 7 edges, when n is 0 or 1 mod 14, it's easy. When it's 7 or 8 mod 14, it's more difficult. For the number of edges being 8, you only have the case 0 and 1 mod 16, and not the ugly case, which would be 8 and 9 mod 16, because the divisibility condition is not satisfied then. So here is the situation. What we are looking at, that's what we will be solving. Disconnected bipartite unicyclic graphs on 7 edges and more than 8 vertices. What they first the current status of progress that is being made in other remaining graphs with 7 edges. Brian Freiberg and his students are working with tripartite graphs of 7 edges and 7 vertices, and Aidan and myself, we are working on unicyclic tripartite graphs on 7 edges and more than 7 vertices. And this is basically done already, but not written up. Bicyclic graphs. It's not like you are riding a bicycle and do your graphs. It's just the graph contains exactly 2 cycles. And this is really more difficult than the unicyclic ones. And that's why we had to ask Alex Rosa, the great Alex Rosa. You will hear about him on the next few slides, and Mariusz Meszka from Krakow to join forces with us, because there are some special techniques needed that we are not really that good at. So what we will be showing here is that these three graphs, these are the only graphs in that category, always decompose the complete graphs when this condition is satisfied and the number of vertices in Kn is large enough to accommodate the graphs. So unicyclic graph again means there is exactly one cycle and our graphs are disconnected. The same graphs, Unicyclic disconnected graphs with 8 vertices were already solved by my former student Michael Kubesa and myself. And the reason why we left out these 3 is kind of bizarre. Rita already mentioned that I like, among other things, that I like beer. And that's true. And my friend and collaborator Michael likes beer even more. And we were talking about this, that we would attack this problem, unicyclic disconnected graphs. And we decided that there would be probably too many graphs in that category. So we need to split it evenly between into 2 parts. And because I was just drinking my 3rd beer and Michael was drinking maybe his beer number 5 or 6, we somehow miscalculated. And the first category, 7 or less, is way bigger than this one, than just the 3 graphs that are left, which is good because, you know, if you work with students, you don't have to get your problem too messy. So how we go about this? How we go about these decompositions. So here is the necessary condition again. And we will actually split the proofs, the constructions into really 4 different categories depending on the number of vertices being 0, 1, 7, or 8 mod 14. The first 2 cases will be solved by using labelings that were introduced in 1965, 66, when Alex Rosa was writing his PhD thesis, and he published the result in 67. And we will be using cyclic decompositions here. Cyclic means, in simple terms, I will take a copy of my graph, put it within my complete graph that the vertices are drawn on here on a septagon or a polygon where every vertex of Kn is a vertex of the polygon, and I will rotate my graph through it. So even, you know, you can view it geometrically that you are moving the same shape by certain split of 360 degrees divided by the number n of edges in the complete graph. You can disregard these little numbers for now. We will again look at this part of the definition a little bit later. Now let's see what techniques we will be using. So as I said, they are all based on Alex Rosa original labelings. And what we will do, we will label the vertices of the graph with the numbers from basically the group Zn, where n is the number of vertices in my complete graph. And I will calculate the length of every edge. Here in this graph, or this drawing of the graph, the calculation is easy because I always take the larger number and subtract the smaller number and get the length. However, it's not always the case that you can do it for graphs. And what you see here is a different way, because 6 minus 0 would be 6. But really, if you take 6 as and its inverse in Z9 here, the inverse is 3, right? And again, without using abstract algebra, without using groups, I can say that the distance between these two vertices is the shorter distance along the polygon. So I do 1, 2, 3 steps, so the length of my edge would be 3. Here again, it's not 6 minus 1, it's 1, 2, 3, 4. So the length of this edge is 4. This is the most general labeling row. Sigma means I am calculating all edges in the natural way, all edge lengths, 5 minus 1. So sigma labeling is a special case of row labeling which is more restrictive, but more friendly for decompositions of bigger graphs. So here are the definitions, formal definitions of the labelings. One particularly interesting and probably best known is graceful labeling. And that is the labeling where you only can use for vertices labels from 0 to the number of edges in that graph. And why is it best known? Because there is this famous graceful tree conjecture that says that every tree has a graceful labeling. Now, alpha labeling is something that we will use in some modifications in our constructions. It's graceful labeling with the property that the labels are split such that one partite set, all labels are smaller than labels in the other partite set. We will see an example here. This is an alpha labeling of my graph that I was showing before. And what I can do here is I can draw a line here between the two partite sets, and you can see the labels are 0 and 1 in one of them and 2 and 4 in the other. Why is this labeling important or useful? Well, the labeling so far only allow us to decompose a complete graph where the number of vertices is 2 times the number of edges plus 1. Okay, but what if I want to decompose a bigger graph? A graph that has number of edges divisible by 4 as well, but is bigger than 9. So there are some other generalizations of that alpha labeling by Alex Rosa. And this is the generalization discovered by Saad El-Zanati and his collaborators. Look at this graph. This is a bipartite graph again. And you can draw the line here and notice that you have a label in this partite set bigger than this label here. But they discovered that you don't need that condition to be satisfied globally. It's only important to have it locally. You have this vertex has 2 neighbors and they are both bigger. This vertex has 2 neighbors and they are both smaller. You don't have a vertex that would have one bigger and one smaller neighbor. And with this labeling, you can do the same trick in slightly different way than what you do with alpha labeling. So here is alpha labeling in action. Here is my graph with 6 edges, and here is my alpha labeling, right? I split the partite sets. The labels here are 0 and 2, all smaller than all these labels here. But what I can do now is, what if I want to decompose K37? I want 3 copies. I want a graph with edge lengths to be, well, this minus 1 divided by 2, which would be 18, right? So I do 3 copies of my original graph and keep the left partite set fixed and stretch the right partite set by what? By 6, because I have already all my lengths here. So if I stretch this by 6, I will get length 6 more in each edge. And I do it once again, and I get lengths from 13 to 18, and I'm done, because now, by the previous theorem, I have edge lengths from 1 to almost half of this number, and I can rotate the whole thing through the complete graph K37. With the theorem by Saad El-Zanati and others, the stretching is done differently. We will not need it, so I'm not going to go into details. But there is one thing actually I forgot to mention, and I need to mention it. Alex Rosa was my PhD advisor. So I had the great Alex Rosa as PhD advisor and friend forever after. We talk every week on Zoom or something else, and he has been like one of the most important figures in my life. Anyway, what was that? Sorry, I hit the wrong button. I hit end rather than next page. Oops. Where are we? Here we go. Okay. So now back to our other methods. This method was good for the complete graph that is 2 times the number of edges times a constant plus 1. But what if, say, for my 7 edges, another candidate for decomposition would be K8 or K16. That means the number of edges times 2 or times an integer plus 2 rather than plus 1. What we do in this case is the following. This is called one rotational decomposition. And what I will do, I can use it if I have a vertex of degree 1. So here I am decomposing what? I have 9 vertices here and the 10th vertex here. And I will here label my graph as before. I have 9 vertices, so I can use lengths from 1 to 4 for this complete graph. And this hanging edge is fixed at the 10th vertex. And if I rotate the whole thing, this red edge will go between infinity and continuously every vertex in this K9 graph. And it can be also used when this graph minus infinity, minus this hanging edge, has one of the good labelings that allow stretching. And we will see in detail how this works for our graphs later. So this is one rotational decomposition. John Fahenstiel, who was my graduate student about 8 years ago, we did a special labeling special case for bipartite graphs with a vertex of degree 1 that allows the stretching that I was talking about. I'm not going to details here. Here is how it works. I will label in my original labeling, which in this case is alpha, but you don't need alpha. You can have something more general, but alpha is good. The longest edge must be the edge with the vertex of degree 1. And now I will stretch my graph 3 times, but in the largest copy with the longest edges, I will replace the longest edge, which would be 15 if I was decomposing the graph on odd number of vertices. I will replace it by that infinity length. and fix the infinity vertex. And then I will rotate this thing through my graph, my complete graph to MK, and this edge will rotate through all the vertices from 1 to whatever that would be here. So that's the method. And we will here use these two methods that I mentioned before for the two easier cases, which are n congruent to 1 and 0 mod 14. And we will use the sigma plus labeling that we introduced, John Farnstil and I. As we say in Czech language, zabít dvě mouchy jednou ranou, which means to kill two flies with one smash. Well, in English, the saying is to kill two birds with one stone. So we will use basically the same labeling to cover two classes of graphs. Here are the three graphs that we are investigating, and they are labeled so that they satisfy the theorem by John and myself. So you can see edge lengths from 1 to 7, and the longest edge is saved for a edge with a pendant vertex. So what I can do immediately with this labeling the decomposition of any one mod 14, because the number of edges, say, here is an example for K43, which is what? A multiple of 14 plus 1, right? 42 plus 1. So 42 divided by 2 is the number of different lengths that I will be using for my edges. And I will simply rotate this whole graph through my K43 and I am done. So the case of n congruent to 1 mod 14 is completely solved for all three graphs. I'm showing just one of them, but the labeling exists for all of them, as we have seen here. So I promised two birds, and the second bird will be n congruent to 0 mod 14, where I just take the edge that was labeled 21 and I label it infinity, and here is what I have. I have the vertices labeled from 0 all the way to 21 in my little K41 now, and this is the vertex number 42, which is not labeled 42, but infinity. And if I rotate it, this edge goes through all these edges between this big complete graph and this vertex. So this was actually the easier part. This was the two cases where you could use labelings without modifications. What happens next is the two more difficult cases. If you look again, 43, that is probably not correct, because it would 43 is what? It's an even multiple, so I need an odd multiple of 7 plus 1 rather than this. So this number is wrong, but what I want to do is, if I have an odd multiple of 7 or odd multiple of 7 plus 1, which will be shown a little bit later, if you look at that number, say the smallest number would be 21. K21 has, what are the different lengths in K21? Well, subtract 1, you have 20 divided by 2, you have 10 lengths, but your graph has 7 edges. So how you do that? You would have to distribute the edges somehow differently. Luckily, for these graphs, we can use the following. So this should be actually 49 here, and I will start with a graph K7 and break it into the Hamiltonian cycle and the complement. Notice that these vertices are black and these vertices are white, and it has a meaning because every black vertex here means that I will put inside here a complete graph K7. So I will decompose later on, and into every white vertex, I will put the complement of K7. That means 7 isolated vertices. And now I decompose these two graphs, and what I get here is a black vertex and white vertex. This will become K7. This edge will become K77, complete bipartite graph. Here, this will be K77. This is shown here. This is one of these edges blown up by fitting in complete graph K7 and the complement of K7. So now I have broken down my complete graph K49 into 7 graphs like that, which is really K14 minus K7, and, well, some number of graphs K77. If in turn I can decompose this and this into one of my graphs, I'm done. So how do I do it? This is easier because I'm decomposing just a complete bipartite graph into bipartite graphs, and I can basically use the same labeling as before and just slightly modify it and find what we call a bipartite row labeling or bi-labeling, which means the edge lengths this time will be from 0 to 6, and every edge length is counted by subtracting the left apartheid left-hand side label from the right-hand side label. So this edge is of length 5 because I'm subtracting 6 minus 1. Here I am doing the calculation, of course, in the group Z7. So I would have 0 minus 1, which would be 7 minus 1, which is 6. I have all lengths, so I can do I can decompose the complete graph K77. Here is the second graph, and here is the third graph. Now, for the graph K14 minus K7, the situation is a little bit more complicated. Luckily, we have one graph in which it will be relatively easy. That's the graph G1. And what I will do is the following. I will construct my graph such that in this complete graph, I have edges of length 1, 2, and 3. And that's all I need in K7, right? In K7, the lengths are 1, 2, and 3. Now, in the complete bipartite graph, there are lengths from 0 to 6, and I'm using just 4 of them, and that is, this is length 2, 3, 5, and 4. The remaining lengths, 0, 1, and 6, will be used later. So I have these lengths here, and if I now rotate the whole graph by moving every vertex one step down, one step down, one step down, these red edges will decompose my K7. And these black edges will use all edges of these 4 different lengths, one at every turn. Now I have 7 copies of my graph here, and I need 3 more copies using the edges of lengths 0, 1, and 6. And for this graph, luckily, it can be done. I can find 3 copies using just these 3 lengths. It becomes a little bit more complicated with the 2 other graphs. where I start the same way. Here is my first copy. Again, lengths 1, 2, and 3, and 4 different lengths here. And I keep rotating it, but not this time 7 times, but only 6. The reason is I cannot build the 3 remaining copies using edges of lengths 0, 1, and 6 only. If I try to use the last edge of length 6, I cannot do it. So what I need to do is I borrow an edge. This edge would normally be, this is length 2. This normally would be in these copies, but I will borrow it from the last copy. This edge will not be used in this graph. It will be used here, and the excess edge of length 6 will be moved to this copy. So now I'm done with decomposition of the complete of K14 minus K7, which is bipartite graph with K7 added here. A similar situation happens here. Here I'm actually swapping one of these edges for this red edge, but again, serves the same purpose. So these tricks allow me to use well-known labelings to decompose complete graph with 7 mod 14 vertices. And I need to look at, oh, here is another way that I was doing with Andrew for graphs on 5 edges. That's what I mentioned was solved between the first version of this presentation and now. As you see, I am decomposing something slightly different. I am using an edge here in this partite set, an edge in this partite set. So rather than decomposing the K10 minus K5, where there would be the full K5 and there would be isolated vertices, I am decomposing a C5 made of edges of length 1 here, and another C5 made up of edges of length 2 here. So I am decomposing, there should be K55 union 2C5. And it works a similar way as in the previous case, where these graphs correspond to the black Hamiltonian cycle, and the remaining graphs are just the bipartite ones. So that's another way of doing it. Now, the most difficult case is I'm not going to do the calculations here. What we need to do is notice that we don't have a multiple of 7, the number of lengths. So we will really do, what we will do here is 2 different starters. I will use, oh, what is this? Funny, when you do colors, it changes the layout. Okay, so what I will do, I will use the edge lengths 1, 2, which is the shortest 2, and the longest ones, 7K plus 3 and 7K plus 4, for a special starter, and then the remaining ones that are consecutive from 3 to 7K plus 2 in the same way as before, stretching and covering the remaining edges. So what I am doing here is really I decompose the complete graph on 8 mod 14 vertices into this circulant. Okay, I am using edges of length 1, 2, 7K plus 3, and 7K plus 4. And then I will be decomposing the complement of this circulant. Notice that the edge of length 7K plus 4, the length is half of the number of vertices in the complete graph. So this edge is not present 14K plus 8 times, but only 7K plus 4 times, the half of the, because if you rotate the edge halfway through your complete graph, it overlaps, this copy overlaps with the first copy. So here is an example of using edges of length what? 3, 4, 5, 6, 7, 8, 9. Didn't I say? Oh, no. These are, of course, the regular starters. That's the starter, basically with alpha labeling slightly stretched. Normally in alpha labeling, I would have 1, 2, 3, 4, and so on, but I stretch it by 2 because I will be using edge lengths 1 and 2 in my special starter. So this can be now stretched to do as many copies as I need. And all I need to do now is find a decomposition of that circulant into my graph, one of my 3 graphs. This one is easiest because this one is symmetrical. So I will do this. This is length 1, length 2, and length, what would that be? 10, and this is length 11. This will be present only 11 times. All other lengths are 22 times. And if I rotate this 11 times, I get here and I'm done, because I have used this edge, moved all the way halfway through my complete graph before hitting the edge of length 2 here, which was moving all the way up to here. And the same applies to the edges of length 1. This goes from 0 to 1, then from 1 to 2, ... then to, this is wrong. This should be 10, from 10 to 11, and I am done. For the 2 other graphs, it's a little bit more complicated because it's not symmetrical. And you see this edge will, or let's look at the red one. This edge will chase this green one, and in this copy, I will have my my red isolated edge that would be the last copy. So I'm using this edge twice, and there is an edge from 11 to 13 that is not used at all. All I need to do is carefully swap this edge in the next to last copy with another one. And again, it's a technicality. It can be done. I, of course, have shown it in the paper. Similar situation is for the remaining graph. And by using the rotation, except for the last one, I have done everything. There is also a alternate construction using a similar decomposition as we did before, except I will be decomposing K44, and one of these black vertices and one of these white vertices will become K8 rather than K7. Okay. So this will be actually a graph where I will have K8 here and complement of K7 here, and I need to decompose this, and I will do graphs K77 and also graph K8A7. It is useful for some other graphs. In this case, the construction we have shown is more useful. This one would be very difficult, so we chose that one. And that's all I wanted to show. Okay, here is the references, and here is my thank you page. Thank you for your attention, and I'm open to questions.
Thank you very much. So I don't know if we have some questions from somebody. I cannot see everybody, so I don't know.
Well, that's good because I went overtime, right? This was my 30-minute talk that lasted 47 minutes. So
But it's okay. So I don't know if somebody have some observation.
some new attendance. Hello.
Okay, if no, I have a question. This composition, I was thinking in a small case, etc. Is unique, or
Oh,
you can have
definitely not.
no,
Definitely
you can
not.
have different GI that give
Sure.
us this
Sure.
block.
Even with my methods that are kind of simple, I could find different decompositions by labeling my graph before I start stretching it or rotating differently. But there are design theory methods that Alex Rosa and Mariusz Meszka would be using. And these are very different. They are based on transversal designs, decomposition of transversal designs and complete graphs. And that's what they were actually using for that case, 8 mod 14, as I mentioned at the beginning, for the bicyclic graphs. So they are very, very different.
Okay. And I have one more question, because in this group, we like a lot circulant graph. So immediately that you give your definition, I think, of course, in circulant graph. So my question is if there is some like characterization of which circulant graph has this type of decomposition. Or, because you put one example in one of the last examples, you have one circulant, but
that's a good question, and that's a question that I asked myself a few days ago, because of course more general results would follow from that. And I vaguely remember that Saad El-Zanati was once giving a talk about decompositions of circulants. And I was trying to find the paper yesterday, and I only found one paper that did not cover the same thing that he mentioned at the conference. So I must ask him, it's probably an unpublished result that they were working on and then abandoned. So there is something known, but not much about circulant decompositions. But you can use, if you have a circulant with consecutive lengths, then you can apply the labeling techniques as well, as long as the number of different edge lengths in your circulant is a multiple of your number of edges in your graph, then you can use the techniques.
Because I was thinking that for example, it is very interesting for me this in this circulant graph, this counterexamples of the Adams conjecture, where you have the set of salt that define the circulant graph are different, are not, you cannot obtain one for a multiplication for the other, but the circulant graph are isomorphic.
Yeah.
So so I was thinking that it would be very nice to see this construction of this block. Yes,
well,
if you
this would be a topic for my next graduate student if I were not retiring after this semester. So
okay.
I may try to find some graduate students maybe in Poland to work with me when I'm retired, closer to home.
Okay. Okay, so these are all my comments. I don't know if we have another comment. Maybe later. Sometimes we have a question later when the people see the videos. So, not Julian. Okay, so thank you very much, everybody. Thanks to Ursula and Dalibor for this nice first day of our CART and for your talks. And we invite you to continue to see the video talk and poster that we have in our channel for the day of today. And we will see you tomorrow, again, 10 a.m. Mexico
My
time.
apology, you will not see me tomorrow. I'm traveling tomorrow, so I will be back on Friday only.
Okay, thank you. But any case, thank you. So, so see you tomorrow.
Yeah,
Bye-bye.
bye-bye.
Bye-bye. See you. See you. Bye-bye.
Bye.
Bye.